All right, so we are looking at improper integrals. This is heavily from Paul's online notes, but we're going to try it anyway. So we're going to do an example, get a little bit confused, and then look at some definitions, some guidelines, some more examples, another theorem. It's going to be great. So let's evaluate this integral. So we have a definite integral from 1 to infinity of 1 over x squared dx, and that can we do that? Whoops. Can we deal with this using what we have? Can we like rewrite this as a power? So we have x to the negative 2 dx. Is that allowed? Can we have our bounds like that? Heck no, because definite integrals need numbers as our bounds. So we're going to just say this is b and limit as b approaches infinity. That's just what we're going to use. So then what do we get? We get the power rule, so we got x to the negative 1 divided by negative 1 from 1 to b, but we can't forget our limit notation, otherwise we have a bad equal sign. So what do we get? Limit as b approaches infinity of negative 1 over b minus negative 1. Okay. And that's what's inside our limit, but minus a negative is plus, so we have negative 1 over b plus 1. But as b goes to infinity, our denominator here goes to infinity, so this number goes to 0. And so we end up with a positive 1. Okay, it's not terrible. So the general idea was just that we, instead of dealing with an infinity in our bound, we're like, hey, let's not do that. Let's throw that into a limit, and then we can deal with just the limit of some variable instead of thinking about the infinity until we have to use the infinity at the end, evaluating our limit. Because definite integrals are limits, and limits are numbers, and so we want numbers. So this is launching us into an idea of convergence and divergence. Convergence and divergence is a really big thing for like the rest of the course. So it's important that we kind of like get okay with we're calling things or referring to things as convergent or divergent. So convergence, improper integrals, these are called improper integrals because their bounds are not definite. There's infinities in the bounds, so that gets a little hairy, so they're called improper integrals. But they're called convergent when we have a number that exists. We get a finite number. So that's when our limit exists, then our integral is convergent. If our integral is not, does not exist because our limit does not exist, then we call that, improper integral divergent. So our options are convergent if it's a number, or divergent if it's not a number, if it's infinity, minus infinity, or if that integral, doesn't exist. So, convergent and divergent. And we're going to be using those a lot, when we have things converging versus diverging, that has meanings in other contexts as well. So, we have, and this is just formalizing what we had earlier, we have our definite integral where we have some parameter t, then we can write this as a limit, like swapping out our bound with our parameter t, and that's going to be okay. And that's also going to work with negative infinity if we're going down below. That is also totally fine. We have our parameter t or whatever else going to negative infinity, and then we can swap out that bound with the with what we're putting into our limit. And we can also split up if we have infinities, minus infinities in our bounds, then we can split up our that like super improper integral into two different parts with a c in the middle, and then do limits on both of those with different parameters, and that is okay. But that will imply that we have convergence for our sum, because when you have a number plus a number and you get a number, then you're good to go. This does require that both of these converge. Otherwise, if you have like a number plus infinity, you're not going to get a number, you're going to get infinity. So if either of these diverges, then this one is going to diverge. So for this example, we're determining if this is convergent or divergent, and if it is convergent, find its value. Okay, so we're just looking for, is it a number? And if it is a number, then what number? And if it's not a number, then say it's divergent. So we have our upper bound is infinity, so let's say that b approaches infinity for our integral from 1 to b of 1 over x with respect to x. And so we can evaluate our definite integral before we have to deal with our limit. So what's that? Natural log of x from 1 to b. And so that's limit as b approaches infinity of natural log of b minus natural log of 1. Natural log of 1 is 0, right? Because e to the 0 power gives us 1. And oh, do you do this as the snail? So you have log base e of 1 equals what? And then you do the snail, where you have e to what power gives you 1. That's how I think about logs, like almost every time. Okay, so we have natural log of b, and b goes to infinity. So what's the end behavior of a natural log? It keeps on going up into infinity. So what we get is infinity, which does not exist. So then this integral is divergent. And I would, slap a picture of that book, that Divergent book movie series. But, I lost that picture. It's somewhere. But divergent. Okay. So, here's something we're just going to say. We're going to justify it later. That if we have a is greater than 0, so this is greater than 0, and we're dealing with something that's like a function kind of like that. So you're dealing with a's, so your starting point is somewhere above 0, and you're going to infinity. You're convergent if your p is greater than 1. So if you have 1 over like x to the 1.000001, and then you're going from a to infinity, this is going to converge. But if p is less than or equal to 1, like we saw in this example up here, p is 1, then this diverged. And we're going to justify that a little bit later. So, let's determine what happens here. Well, our lower bound is now our like tricky thing, but it's okay, we can still handle it. So let's rewrite this as a limit as b approaches negative infinity from from b to 0. And a reason I like using b is because it's very forgiving. I can, like, if I accidentally write it as something else, I can, make it into a b. But you can use t, you can use like f, you can use q, like whatever, but t or b are more typical. That's all. Okay, so we got 1 over root 3 minus x dx. Okay. Now, so there's a few ways we can proceed from here. We could do a u substitution and think about this in terms of that. That's one option. We can just do the u substitution in our minds, where we say that, okay, we got something to the negative 1/2 power, and our chain rule is like, okay, so we can rewrite this as limit as b approaches negative infinity of b to 0 of like 3 minus x to the negative 1/2 power. Treat this as a u, like we're thinking that this is a u. And then we go from there. Yeah, I think we can do that. So let's do limit as b approaches negative infinity. So we get what, 3 minus x, and then we add 1 to the power, so we get 1/2, and divide by our new power, so that's multiplying by 2, because dividing by a fraction is the same as multiplying by the reciprocal. And then, in order to deal with our chain rule, we gotta negate everything, and we're going from b to 0. Okay, this is like not so bad. Let's plug stuff in. We got limit as b approaches negative infinity. So negative 2 times 3 minus 0 to the 1/2 power minus negative 2 times 3 minus b to the 1/2 power. Sorry, I ran out of space there. So then what happens? Well, this first part is a number, right? So we get negative 2 times root 3 plus 2 times 3 minus negative infinity to the 1/2 power. That's infinity, so that's gonna be infinity. So this integral is I can't spell divergent. Divergent. It's written right there. That's what I looked at. Okay. If you're thinking to yourself, hey, that was like a lot of work, and I didn't feel like I needed to do that really, you might be right. So if you say that u is 3 minus x in the beginning, so then du is negative dx, then you can do like some substitution here so that you get, eventually you get out, what, like negative, well, 3 minus negative infinity is going to be positive infinity, and then 3 minus 0 is 3 of negative 1 over u to the 1/2 power du. And then you can look at this and think back to what we said before, where we have like x to the p, right? But in this case, we have u to the 1/2, and this 1/2 is definitely less than 1, so then we get divergent. That is totally valid. But you still have to show this part, which is essentially what we did here. But that's okay. Alright, so in this one, we got example 4, where we're looking at, again, is it conversion to divergent? And if it's conversion, find its value. So, is it a number or not a number? And if it's a number, what number? We now have bounds that are infinite on both our upper and lower bound. So we need to break this, we need to break this up. And what's our favorite number that's between negative infinity and infinity? 0, yeah, absolutely. So let's break this up into integral from negative infinity to 0 of x times e to the negative x squared dx plus integral from 0 to infinity of x e to the negative x squared dx. Alright, so let's look at them separately. I guess we should do this one in red and stuff. So let's look. Limit as b approaches negative infinity of b to 0, xe to the negative x squared dx. Okay. And then, well, this looks like a u sub, right? Where we say that u is negative x squared, so then du is negative 2x dx. So then we can write this as limit as b approaches negative infinity of, and I'm going to leave these in terms of x's, x equals b, x equals 0 of, let's see, negative 1/2 e to the negative, no, e to the u du. Yes? And then, well, I could also sub that back in, right? Well, I guess u, this part is just 0. And then b is going to be negative b squared. Okay. And now what? Well, we can just plug that in. So we got limit as b approaches negative infinity, negative 1/2 e to the 0 minus negative 1/2 e to the negative b squared. Okay. E to the 0 is 1, so that goes away, and we have a negative 1/2. We have this b to the negative b squared going to negative infinity. So this whole thing is going to 0, right? Because what happens to our e? That goes away. So then we end up, this is negative 1/2. Whew. And then for this one, oh, that's interesting. All right. So for that one, let's bring it down here. We have limit as b approaches positive infinity of 0 to b x e to the negative x squared dx. And that we can rewrite as limit b approaches infinity of, what did we do before? Negative 1/2 e to the negative x squared. That's essentially what we had, right? From 0 to b. And so what does that give us? That gives us limit as b approaches infinity of negative 1/2 e to the negative b squared minus negative 1/2 e to the 0. And that goes away to 1. This goes away to 0. So then we're left with positive 1/2. So now when we add these up, add these two up, negative 1/2 plus 1/2 is 0. So we got conversion. Got conversion, and we got this to be 0. Conversion. Cool. And you thought it would never happen. So we have, what happens if we're looking at one-sided limits? It still works. We can use one-sided limits and be okay, even if we have an interval where our function isn't continuous on the closed interval, because we can just use one-sided limits and we're good to go. And it works in both directions, approaching from the left, approaching from the right. We are still good to go because limits are numbers, and so it's okay. If we have something that's not continuous at somewhere in between, so like this, you got A and you got B and then you got C in the middle, so you got like a hiccup or something, and you can figure out your definite integral with two separate one-sided limits, so you're still okay. And if you have discontinuity at the ends, that's okay too. You can still handle it, but again, you need to have convergent on both of the things you're adding together, otherwise it breaks math and you don't have a convergent integral on the whole interval. So what happens here? Again, we're looking convergent or divergent, so is it a number or not? And if it is convergent, if it's a number, then what number? But just thinking about its sign from like -2, so that's, sign is going to look like that, right? But then like going from here to infinity, what do you think is going to happen to this definite integral? What's the area under the curve? It's going to vacillate between like positive values and negative values. At some point things are going to be zeros, because this oscillating component, that's just it's gonna give us something that doesn't have an area that we can say is a particular number. But let's, like, intuitively, that's fine. Let's actually show it. So we got a limit as b approaches infinity of our integral from -2 to infinity. It's b. We change it, Mrs. Contreras, sine of x dx. So then we get limit b approaches infinity of negative cosine of x, right? Because derivative of cosine is negative sine. So then integral of positive sine is negative cosine. Negative 2 to b, so then we get limit as b approaches infinity of negative cosine of b minus negative cosine of negative 2. This is a number, this is not. So we get divergent. Not a number. Okay, so here, if you plug in 3 there, like if you're thinking about this function as your bound, with your bound as 3, then you're going to get 1 over root 0. So 3 isn't going to be part of like where our function is defined. But that's okay, because we have one-sided limits. So let's one-sided limit this improper integral, and what do we get? Is it an improper integral? Yeah. So we got limit as b approaches 3 from which direction? We got 0 to 3, so we're approaching 3 from the left, of integral 0 to b of, and we're going to rewrite this as 3 minus x to the negative 1/2 power, just because I feel like that's easier to deal with. And that gives us limit as b approaches 3 from the left of what? We have negative 2, 3 minus x to the positive 1/2 power from 0 to b. And we did that earlier, right? That was what we did earlier. Okay, so what do we get? Limit as b approaches 3 from the left of negative 2, 3 minus b to the 1/2 power minus negative 2, 3 minus 0 to the 1/2 power. So what do we get? We get positive 2 root 3, because this part goes away, this part goes away, so we have 2 root 3. So that's convergent, and we found the value, 2 root 3. Okay, for this one, we have this, which is discontinuous at x equals 0. So we got to break this up into 2 different parts, right? So we get this is going to be integral from negative 2 to 0 of x to the negative 3 plus 0 to 3 x to the negative 3. And so we're going to get these as 2 separate limits as b approaches 0 from the left of negative 2 to b, execute negative 3 dx. What's that limit? B approaches 0 from the left of we got x to the negative 2 over negative 2, because we add 1 to the power and divide by our new power. So we got that. And then what do we have? Limit as b approaches 0 from the left of negative 1 over 2 b squared minus negative 2, so that's what, 8? 2 times 4. Okay. But what happens here? If we're looking at 1 over 0, that's undefined, but it's going towards infinity, negative, approaching 0 from the left, but that's okay because it's squared, so then we have negative 1 over 2 times a very small number. So it's going to be positive, so then negative over positive is going to be negative infinity. Womp. So, even though we didn't even bother with this other part, we just evaluated this and this is negative infinity, that means that the sum is going to be divergent. Alright, so this is Gabriel's horn. Gabriel's horn is taking the function 1 over x and revolving it around the x-axis. So how can you find the volume and how can you find the surface area of this solid? What can you do? So, well, we have volume. Volume is going to be pretty straightforward, right? And let's look at where we have our x from 1 to infinity. Okay, so let's just start it at 1 and get us to infinity. Then we're going to have our integral, where it are bounds, 1 to infinity of pi r, which is 1 over x squared dx, right? So that's this part. And then we're getting that, this sketch is better. So let's evaluate this, and we can see that this is going to converge, right? Because we're going to have our p, our power of x in our denominator is going to be 2, and that's going to give us conversion. So what do we get? Limit as b approaches infinity of pi x to the negative 1 over negative 1 from 1 to b. And what does that give us? That gives us limit as b approaches infinity of pi over b, negative pi over b, minus negative pi. That goes away, and so we just get pi is our volume. So the volume of this shape is pi. What about the surface area? How do we find the surface area? So in order to find surface area, what do we need? We need integral surface area. 1 to infinity of, 2 pi times our function, which is 1 over, but we're revolving around the x-axis, so we need this in terms of our y value, times root 1 plus, and what's y prime? D y? No. Yes. So now let's write this out. So we got 1 to infinity of 2 pi, and then our y is 1 over x. 1 plus derivative of 1 over x is negative 1 over x squared. Oh, I forgot to square this. Squared dx. So then what do we get? Wait, does this? I think this does. So this ends up with, okay, so this is like, I don't know if we can handle this yet. So maybe we need some other stuff. So we probably want, we don't want to handle integrating that. That seems pretty gross. But what we can do is compare it. So is there something that we can say, okay, we know that we have this, kind of like how we had the squeeze theorem, right? Is there some way that we can say, okay, let's compare this to something that we know and see if this converges or diverges? And the answer is absolutely. So our comparison theorem is, so if we have f and g are continuous, and you know that they're continuous, and you get an interval, and you also know that f is less than g, so you got f is over here, g is over, oh no, sorry, flip that. We got f is less than these, so g is there, f is there, and then 0 is over here. Then you know that if f diverges, then whatever's greater than it is also going to diverge, right? Because the area of something smaller, if that diverges, it's not a number, then anything bigger than that is going to also diverge. And you also know that if you do have converging on the like top function, if you have converging g, so g's improper integral converges, so it's a number in R, then the function that's less than that, whoops, just erased it, the function that's less than that is also going to converge. This is going to converge. So, that's nice, because if we're looking at this, can we write this a little bit cleaner? Can we say, okay, so this is 2 pi integral from 1 to infinity of 1 over x times root 1 plus 1 over x to the 4th. Okay, now looking at this, do we have something that we can compare this to? So we have 1 plus 1 over x to the 4th. So this value, for any x value that we have, this what's in here, is going to be a positive number greater than 1. So this is going to give us 1 over x, which is something that we know diverges, and then times something else that we know is greater than 1. So is there a smaller function than this that diverges? And the answer is absolutely, right? 1 to infinity of 1 over x, that diverges. So we know that this diverges because this is greater than 1 over x. What's in our integrand right here, which I guess I could highlight. So this integrand, that's going to be greater than 1 over x, and since we know that 1 over x diverges, then we know that our surface area of Gabriel's horn is infinite. So this surface area diverges. And some people say that this is a paradox because you got a volume that's finite, you got pi volume, and then you got a surface area that's infinite that diverges. So if you want to journal about that, that might be fun. All right, last thing. So let's use the comparison theorem to show that this diverges for all p greater than 1. Well, we know that we have 1 to infinity of 1 over x dx that diverges. And so, because of natural logs, right? It's because the limit as b approaches infinity from 1 to b of 1 over x dx gives us the limit as b approaches infinity of natural log of x 1 to b, which is limit b approaches infinity, natural log of b minus natural log of 1, which is infinity. So we know that this diverges. So by the comparison test, or by comparison theorem, since we know that 1 over x is less than 1 over x to the p for all p that are less than 1, right? Yeah. Because when you have like 1 over x versus 1 over like root x, it's going to be a bigger function. And this is for all. Mathematicians have funny symbols. This is a there exists, this is for all. There's like element of, they're all really fun, but not necessary for right now. So then we know that 1 to infinity of 1 over x to the p dx diverges for all p is less than 1. All right.